Hi, today we'll go through nitrogen compounds concept test. So first question, although it seems that arginine has many basic amine groups, only 2 of them are truly basic. So as you can see for arginine, we have 1, 2, 3, 4 amines, but only 2 of them are truly basic, right? So of course it will be the 2 most basic amines, right? We know that this amine is definitely basic, right? So what about the other one? Which one of this is the most basic? So if you can recall what we have learned in nitrogen compounds, right? We have learned about the Ariel rule in predicting stability of ions, which we can use to predict the basicity, right? So first is atom, followed by resonance, right? So we go back to our question. For this question, we can't really use atom because all of them are nitrogen. But can we use resonance? The answer is yes, right? We can use resonance. So now if we compare these 3 nitrogens, we can see that for this nitrogen, right, it is actually conjugated to the double bond, right? So it can actually resonate. It's just like your phenylamine, isn't it? This is your phenylamine. Can you see that this part is the same as this part, right? So that's why it can resonate, and I've already mentioned that resonance will cause the lone pair to be less available. Less available means it will be less likely to attack a proton, means that it is less basic, right? So this is less basic. Same thing for this, right? It is less basic because it can also delocalize, right? It's the same idea. Both can delocalize. So now the most basic amine out of these 3 is actually the amine on top, which is this, right? If you can recall, I already mentioned that this, I mentioned this before, right? This nitrogen is actually sp2 hybridized. So this lone pair cannot delocalize because it is perpendicular to your pi orbitals. So if you were to draw this part, you will look something like that, right? This is your carbon, nitrogen, nitrogen, and your hydrogen, right? So the lone pair is actually perpendicular to this pi orbital, so there's no way for you to delocalize. Okay, so now you already settled the nitrogens which are basic, right? We'll just assign their basicity. Okay, so if you were to look at these 2 nitrogens, right, we know that it's either this or this. So we look at our ARIO rule again, right? Atom, we can't really use A because both are nitrogen. R, we can't use R because this one, the lone pair cannot delocalize, and this cannot delocalize, right? I already said just now. So we look at I, which is your inductive effect, right? So I've already mentioned this during lesson that for this nitrogen, there is this electron withdrawing carboxylic acid group here, right? Why is it electron withdrawing? Is because this carbon has delta plus, delta minus, right? So this delta plus actually withdraws electron and thus exerts a negative inductive effect. So therefore the lone pair is less available on this, right? So what about this nitrogen? For this nitrogen, right, if you can recall, just now we drew resonance structures as such, right? This is just like your amino acid, if let's say you are confused. So it's more or less the same concept as your carboxylic acid, right? So from this resonance diagram, we can see that electron density is actually flowing towards nitrogen, right? So we can draw another resonance structure on this side, and it shows the same thing. So therefore, we can see that for this nitrogen, electron density is actually flowing towards it, right? So flowing towards it means that its electron, its lone pair will be more available, right? If it's more available, that means it will be more basic. So with these 2 concepts in mind, right? We can assign the two pKa values, right? So we know that this is more basic, this is less, right? So we know that more basic means that its pKa is higher, right? Which means this should be 12.48, and the other one, NH2, should be 9.04, and of course your carboxylic acid will be 2.17, and there we have our answer, right? So this question tests you on your ARIO rules, right? As well as your resonance structures. So you can just explain your answer briefly, right? Let's look at the next question. Draw the major and minor species present at pH values of 1, 5, 10, and 14. So I already taught you this in lesson as well. So let's do the two easiest one, pH 1 and at pH 4, right? Like what I said, pH 1 is very, very acidic, so everything is going to be protonated. Of course, everything means these three lah, not all this, right? We already said that there are only two basic groups, right? So in order to protonate everything, this is what we'll end up with, right? NH2 plus, right? The trick is just to add a H plus. So this is our chain, followed by NH3 plus and our COOH. And pH 14, everything that can be deprotonated will be deprotonated, which is just that carboxylic acid, right? Basically. So here is NH, NH, NH2, COO minus, right? Now, what about at pH 5? If we were to look at our assignment, we can see that at pH 5, right, it is more basic than this value, right? And it's more acidic than this value and more acidic than this value. So what we have to do is that we will have to protonate this, and deprotonate this, right? So this is what we end up with. NH2 plus NH, NH3 plus COO minus, right? So let's look at pH 10 now, right? For pH 10, same thing. We can do the same analysis. Erase this first. pH 10, right, is more basic than this. It is more basic than this, and it is more acidic than this. So what we are going to do is that we are going to deprotonate this, right? And then we are going to keep this as it is, since it's its most basic form already, and then we are going to protonate this, right? So this is what we'll get. H2 plus NH, NH2, COO minus. Okay, let's look at this part. Sketch the pH against volume graph when 10 cm³ of 0.5 mol per dm³ of fully protonated arginine is titrated against 0.25 molar of the strong base MgOH2. Take note that for this case, we are assuming MgOH2 is a strong base, right? So this is just the assumption. So now let's look at the molar ratio first, right? This is 0.25 mol per dm³ of strong base, and this is a dibasic base, right? So therefore, it is the same as saying that the amount of OH minus that is present is 0.5 mol per dm³, right? Since it's dibasic. So therefore, we can just add equivolume of this to protonate this, right? So after we have established that, we can go ahead and draw our rough pH diagram, right? So now, as stated, that you have the fully protonated form and you are deprotonating it, correct? So therefore, your graph should be in this direction. So let's go ahead and draw it. So this is what you will get, and you should have 3 pKa values, right? Because your arginine have 3 pKa values, right? So therefore you should have 3 of these, right? 1, 2, and 3, right? So the first one is quite simple. It is just your 2.17, right? The lowest one, followed by the second one here, which is your 9.04, and your last one here, right, which is your 12.48. okay, right? So how do you calculate the initial pH? So we know that initial pH, if you can recall from ionic equilibrium, right, the equation is just pH equals to negative log square root Ka times the concentration of your arginine, right? So I just write Arg, right? So the concentration of arginine is already given 0.5 mole per dm cube. Ka you have to find out from 2.17 here, right? Since it's the most acidic one. So Ka is just 10 to the power of negative 2.17, and you just plug in the equation, right? I'll leave it to you. So now we have to fill in the volume of NgOH2 used, right? So just now we already say that these two are the volume, right? They are equivolume, since by stoichiometry they are the same. So therefore the volume required for here is 10 cm cube, here will be 20, here will be 30, right? And so on. Remember to label your axis, right? So this is your pH graph. Take note that you don't have to calculate this value, this value, this value, because the question never asks for it, right? But if you want to calculate for it, go ahead, since you already learned how to do it. So this is it for part C. Okay, now for part D, deduce the pH at which arginine is neutral, right? So now if you were to look at part B, right? For at pH 1, the net charge is +2. At pH 5, the net charge is +1. At pH 10, the net charge is 0. And at pH 14, the net charge is -1, right? So we can see a gradual decrease, a stepwise decrease in the charge, right? So this hints you that the Pi must lie somewhere around pH 10, right? So if you can recall from what we have gone through, you can actually deduce it if you draw the pH meter, right? The way they drew it, and the shortcut is just to add the two highest pKa, right, which is 12.48 plus 9.04, and then you divide by 2, and then you will have the answer, which is 10.76. Either ways you will get the same results, right? You can either draw the pH line or just use this method directly. So the Pi will be 10.76, which means that arginine will be neutral at pH 10.76, right? It's just this simple. So let's look at the next one. Prof. Liu from NUS has recently synthesized the following molecule using arginine. Suggest the product when the following compound is reacted with concentrated HNO3 and concentrated H2SO4, right? So it's quite obvious that under acidic conditions, all the basic groups will be protonated first, right? So you have 1, 2, 3, 4 basic groups, right? So all of this is gonna be protonated. So you're gonna have something like this first, right? Remember all your positive charges as well as the ring, right? NH4 plus here. Okay, so is this the end? Sorry, this should be 3, right? Is this the end? The answer is not the end yet, right? So this concentrated HNO3 and concentrated H2SO4 hints you that a electrophilic substitution should occur to the ring, right? So the question now is, where should it substitute to? Okay. Now if you only focus on the ring over here, right, you can recall that, or you can refer to your data booklet that NH2 is 2,4 directing, which means your NO2 should be here, right? That is the only place, because this part is occupied and this part is occupied. But in reality, it's not going to happen. So the question is why? So we already mentioned that, okay, if you just focus on this part, right? Just now I already mentioned that when you add con HNO3 and con H2SO4, the first thing that will occur is that this phenylamine gets protonated. So this is what you will get, right? And I always emphasize that acid-base reactions occurs the fastest and they should occur first. So now if you were to refer to your data booklet again, right, is where the magic happens. If you were to refer to this page, you will see that NH2, it's an activating group, but NH3 plus, it's actually a deactivating group, right? Why is it a deactivating group? Because when you have a positive charge adjacent to the ring, it actually withdraws electron density by the inductive effect, right? And just for your info, as a recap, NH2 donates electron, right, by the pi, or you can say the resonance effect, right? While inductive effect, as we always say, it is via sigma bonds, right? So now, okay, so since your NH3 now withdraws electron density, therefore it is a deactivating group and it should direct to the third position. So now if we were to go back to our question, the third position will be here and here, right? These two places. But since it's a deactivating group and we know that nitration should occur only once, since the ring gets deactivated and less reactive, therefore we have to choose whether it's here, is it here or here, right? But not both. So if you can recall from what we have learned in arenes, right? When we have situations like this, we will consider steric effect, right? Just now we already considered electronic, now we consider steric. So if we have the NO2 here, you have 1, 2, 3, 4 groups adjacent to each other, so sterically it is not very favorable, right? So what you'll do is that you'll prefer to add here. So when you add here, you have 2 groups here and you have 2 groups here. They are quite far apart, and sterically it's more favored. So therefore your final product should be this, right, for the ring, while for the rest it's all protonated, like what I have told you just now. Okay, so now we look at question 2. Question 2 is about protein sequencing. So during our lesson we talk about enzymatic hydrolysis as well as complete hydrolysis, right? This is another kind of what we call hydrolysis reaction, whereby it allows us to know the protein sequence, right? So if you turn to the next page, you'll be overwhelmed by so many things, but I'll just briefly explain. It's actually very simple to understand, right? So if you were to look at the first one, you have this compound reacting with your polypeptide chain, right? So this N is a free amino end. It is not bound to anything, right? It's just an amine, free amine. So after this reacts with this, you will have this kind of cyclic structure, and this cyclic structure is known as a PDHR kind of structure, right? Because this is R lah. You can change R to R prime if we call it PDHR prime, right? But the general structure is like that. So now if we were to analyze the first equation, we can see that this reaction is just, right, breaking this bond, and then this part will form the cyclic structure, right? So after you break this bond, you have another free amine, the next free amine exposed, and this next free amine can then be subjected to the same conditions, and once again, right, this bond will be broken, and so on, right, and so on. So this process basically just repeats itself again and again, and then you will have different PDHR structures, right, being produced after every step, right? And then we can just go ahead to detect this PTHR kind of structure. And after we know the sequence of the PTHR structure, then we can go back to deduce our polypeptide chain, right? So this is how it works. So now this is the reaction mechanism of Edman degradation, right? So the first question, given that a nucleophilic addition reaction occurs in step 1 to afford the product, deduce the structure of C7H5NS and give the mechanism, right? So basically it's just asking for the structure of this. That's the key point. So now you know that if, let's say, we have this kind of structure, right, and we have a nucleophilic addition, this is what we'll end up with, right? We can see that the pi bond is being broken and it becomes a sigma bond. So if, let's say, I give you this product and I want you to predict the starting material, you should be able to do so, right? So now C7H5NS, the first step is to calculate the double bond equivalent, or you can say the index of hydrogen deficiency, whatever you call it, right? So in order to calculate it, you just have to take 7 times 2 plus 2, and then you minus 5, and then afterwards you plus 1 for nitrogen, and then you divide by 2, right? Remember, sulfur is just like oxygen, so you have to ignore it, right? It doesn't affect anything. So if you solve this, 2 times 7 is 14, plus 2, 16, minus 5, 11, plus 1, 12, divided by 2 is 6. So you should have 6 double bond or ring whatsoever, right? And this means that you should have a benzene ring, right, which already takes up 4. So you have 2 to play with, right? So what you're left with is just carbon, nitrogen, and sulfur, right? So how do you connect them with 2 double bond equivalents? I believe you can definitely do trial and error, isn't it? Right? So this is one way. So now from here you see that you have this structure, and afterwards you added this part, right? So now, since just now I already say that you should break a pi bond, and you have 2 possibilities, right? One possibility is that your starting material is this. Another possibility is that your starting material is this. Which one you think is more reasonable? The second one, right? Because you cannot have a CS triple bond, just like you cannot have a CO neutral triple bond, right? So in fact the answer is just this. Right? This is your C7H5NS. Okay? So now let's look at the next question. The next part says that they want you to give the mechanism. So same thing. Since it's a nucleophilic addition reaction, you should more or less know how to draw the reaction mechanism, right? Sorry, NCS, I draw wrong. NCS. So I'll just abbreviate it with this, right? So the first step will be this, attacking the carbon, just like your nucleophilic addition reaction. And this arrow, right, should go towards your nitrogen, since it's this bond that's being broken, right? So therefore it should flow to your nitrogen. And also because your nitrogen is more electronegative, right? So remember to draw your delta plus and delta minus. So this is your slow step, right? So afterwards we have a negative charge here, carbon, sulfur, and your NHHR plus, right? Remember, for a nucleophilic addition, the second step is an acid-base reaction, right? And since for this case we have an internal acid and an internal base, you will just perform an intramolecular acid-base reaction, right? And this will afford you your product. NHC double bond S NHR, right? Which is your this structure shown here, right? This one, right? So this is the answer for this part. Next part suggests the type of reaction in step 2. If you were to look at step 2, right, you can see that what's happening is just this hydrogen is being transferred to this oxygen, right? Nothing else. So this is in fact an intramolecular acid base, and you can just call it an acid base reaction, right? Very, very easy. Next, give the mechanism for step 3, show all charges and using curly arrows to show the movement of electron pairs. So if you were to look at step 3, this step, right, we can see that it seems quite complicated, but in fact it's actually very, very simple. It is again a nucleophilic addition reaction, right, whereby this is now your carbonyl that's being added. So the mechanism is just the negative charge attacking here, and the electron pair of this pi bond goes to this O, and this will afford you this product, right? And this is all for this question, right? Very simple, right? Okay, so now D, researchers have recently isolated a cyclic peptide fragment shown below. Draw the PTHR structures obtained after multiple rounds of Edman degradation, right? Just now I already mentioned that Edman degradation allows your protein sequence to be derived. So how about a cyclic peptide fragment? The mechanism actually follows the same thing as previous, right? If we just focus on the first part, the simplified one, we can see that this C7H5NS is already deduced, only reacts with the amine of your amino acid, right? Which is your alpha amino acid, the amine. So if we were to look at this structure, the only amine that is free to react with your C7H5NS is this amine, right? Not this amine, because this doesn't belong to your alpha amino acid, right? This, in other words, if you were to look at this cyclic peptide, it's actually made up of this amine, this amino acid, this amino acid, and this amino acid, right? So it should only react with this group but not the rest, right? You have to establish this first, because it will be important as to which one will drop down first, right? Which one will be detected first. So you just have to copy the PTHR structure, right? So this is your PTHR structure. So I just draw it here, right? I just draw the simplified one to save time. So this is your PTHR structure. So since this is the first fragment to be detected, therefore the first one should be this, right? 1, 2, and H2, right? So this part is actually this part. Okay, so this is the first one, first, right? What about the second one? Now you have to imagine that after I obtain this part, I will have this, right, left. H2N. And like what I've said just now, your C7H5NS will only react with this amine, right? Not this amine. You only react with the amine of your amino acid. So therefore, the next structure will resemble this, right? Will look like this. So this part, right, this part will be this part. Right, this will be the second one, and then the last one is of course this one, right? So after this drops down, you have this, and the last one will be this. This is a bit tricky to draw because there's a cyclic structure, but if you follow the pattern, this is what you will get eventually, right? Let me see. Yes, right, this is what you will get. Okay, and this will be the last fragment that's gonna be detected. Alright,